Before you settle in, pause for just a moment. Right now, you exist at a precise place and a precise moment, and neither makes sense without the other. If you enjoy drifting into sleep while learning how the universe truly works, subscribe to this channel, gently tap like, and leave a comment sharing where in spacetime you're listening from tonight. Now, let your attention soften, because the story of space and time begins long before equations, with humans simply watching the sky. You rest your attention on the simple act of watching. Long before equations exist, humans observe patterns that repeat with steady reliability. You notice the sun rising and setting, shadows stretching and shrinking across the ground, and the slow march of stars across the night sky. These observations require patience, not theory. They form the earliest relationship between where something is and when it appears. Space and time first meet through careful human attention. You imagine standing in an open landscape, watching a shadow move as the sun climbs. The shadow changes position continuously, marking the passage of hours without words or numbers. Early observers learn that distance and duration cannot be separated in practice. A longer shadow means an earlier or later moment. A shorter shadow means midday. The measurement of time begins as the measurement of movement through space. You follow how ancient societies turn observation into structure. Stone markers, aligned carefully with the sun or stars, record repeating cycles. At places like Stonehenge and Nabta Playa, massive stones are arranged to track solstices and equinoxes. These structures are not symbolic guesses. They are physical records of spatial alignment matched to specific moments. Time becomes predictable because space is measured precisely. You notice that early calendars emerge from the sky. The moon's phases provide a natural cycle that links position and duration. A full moon returns after a fixed number of nights. By watching where the moon appears relative to stars, observers connect celestial position with elapsed time. Months are not abstract units. They are patterns written across space. You see how geometry quietly supports these efforts. Measuring land requires fixed reference points. Surveying fields after floods, especially along the Nile, forces the development of consistent spatial measurement. Distance must be known to divide land fairly. But distance alone is insufficient. Seasonal floods return at regular intervals. The timing of measurement matters as much as the measurement itself. Space and time are already cooperating. You follow how Egyptian shadow clocks and obelisks refine daily timekeeping. By dividing the shadow's path into segments, observers assign equal intervals to unequal motion. This requires accepting that time is not simply guessed, but defined by regular spatial change. Each hour corresponds to a position, not a feeling. Precision grows from repetition. You observe the same process in ancient Mesopotamia, where systematic star catalogs appear. By tracking when specific stars rise or set, observers predict seasons. These predictions depend on both where the stars are and when they appear. A star's position is meaningless without its timing. Timing is useless without position. Together, they become a reliable tool. You notice that even early mechanical devices reflect this union. Water clocks measure time by controlled movement through space. Water flows from one level to another at a steady rate. The changing height marks duration. Time is measured by displacement. The principle remains simple and physical. You reflect on how Greek thinkers formalize these ideas. Aristotle describes time as a measure of change. Change requires motion. Motion requires space. Even without modern mathematics, the dependency is clear. You cannot speak of before and after without something moving somewhere. Observation anchors philosophy. You see how astronomy strengthens this bond further. Planetary motion reveals complex patterns that repeat over years. Retrograde motion challenges simple explanations but never breaks the link between position and duration. Greek astronomers record angles, paths, and periods. Their models succeed because they tie spatial paths to temporal cycles. You recognize that none of these systems assume separation. Early observers never treat space as existing without time, or time without space. Every method relies on correlation. A mark here corresponds to a moment there. A cycle in the sky becomes a schedule on Earth. Measurement remains grounded in what can be seen and repeated. You feel the quiet discipline of these early practices. There is no rush to explain causes. Watching comes first. Recording comes second. Understanding follows slowly. The universe offers patterns, and humans learn to listen. Accuracy grows from humility. You consider how navigation across land and sea depends on consistent measures. Traveling from one place to another requires estimating both distance and duration. Early travelers learn how far they can walk in a day, how long a river journey takes, and when stars will guide them home. Routes are planned using both spatial landmarks and temporal expectations. Neither works alone. You observe how sundials spread across cultures. A simple vertical stick becomes a reference for both direction and time. The shadow traces a path that can be marked, copied, and shared. Different latitudes produce different patterns, revealing that timekeeping depends on location. The sky teaches that measurements are local, not universal. You notice that even language reflects this connection. Words for time often borrow from motion and direction. Moments pass, days arrive, seasons turn. These expressions are grounded in observation rather than imagination. Human experience mirrors physical reality. You rest with the understanding that these early systems succeed because they remain anchored to evidence. No assumption is made without repeated confirmation. The sun returns, stars cycle, shadows behave predictably. The link between space and time is not declared. It is demonstrated quietly and persistently. You remain aware that these measurements never claim completeness. They simply work. They allow planting, travel, ritual, and survival. Over generations, confidence grows not from belief but from reliability. Each observation reinforces the quiet partnership between position and duration. This partnership does not demand explanation yet. It only asks to be noticed. In the stillness of repeated cycles, the idea forms that reality may be structured, measured, and understood through relationships that persist even as observers change. You rest calmly with this awareness, sensing that careful measurement opens a path toward understanding deeper connections woven into observable reality itself. You settle into the idea of motion, because motion is where measurement becomes unavoidable. An object at rest occupies space, but it tells you little. The moment it moves, questions appear naturally. How far does it go? How long does it take? These questions arise together, not separately. Motion demands both distance and duration at the same time. You imagine watching a stone roll across the ground. You can describe where it starts and where it stops, but without noting how long the journey lasts, the description feels incomplete. The path alone does not explain the motion. The time alone does not either. Only when you consider both does the movement become meaningful. This pairing feels intuitive because it reflects how the world behaves. You notice how early thinkers begin to formalize this relationship. When distance is divided by time, speed appears. Speed is not an abstract invention. It is a direct description of how space changes with duration. Every moving object carries this relationship within it. Faster motion means more distance covered in less time. Slower motion means the opposite. You cannot define speed without both quantities present. You observe falling objects as another quiet teacher. A stone dropped from rest accelerates downward. This position changes more rapidly as time passes. Careful measurement shows that the distance fallen increases in a regular way with elapsed time. The motion is predictable. This predictability allows time to be inferred from distance, and distance from time. Motion connects them reliably. You reflect on how ancient and early modern observers measure these effects without advanced tools. They use repeated trials, careful timing, and consistent reference points. A slope, a pendulum, a marked path. Each experiment reinforces the same lesson. Motion always links where something is to when it is there. You consider walking as a natural example. You know roughly how far you travel in an hour because your pace remains fairly steady. You estimate distance by duration, and duration by distance. This habit is not a shortcut. It mirrors physical reality. The world allows these estimates because motion binds the two quantities together in stable ways. You notice how planetary motion deepens this understanding. Planets move across the sky night after night. Their paths can be mapped against background stars. Their positions change gradually, and the timing of those changes follows consistent patterns. A full orbit takes a known duration. The orbit itself is a spatial path. The two descriptions cannot be separated. You see how this leads to early laws of motion. Objects continue moving unless acted upon. When forces are applied, motion changes. These ideas emerge from observation, not assumption. To describe a change in motion, you must describe a change in position over time. Force itself becomes meaningful only through its effect on motion, which again requires both space and time. You rest with how naturally this pairing settles into measurement. Even early clocks rely on motion. A swinging pendulum moves through space in a regular rhythm. Each swing marks a duration. The spatial displacement becomes a timekeeping tool. The consistency of motion allows time to be counted. You observe the same principle in rotating wheels, flowing water, and oscillating springs. Each device measures time by tracking movement. The underlying assumption is always the same. Motion repeats predictably when conditions remain stable. This repetition ties spatial change to temporal intervals. You notice that when motion becomes irregular, measurement becomes difficult. A jerking movement makes time harder to track. An uneven path makes distance uncertain. Stability in motion allows space and time to reinforce each other. Irregularity reveals how dependent the measurements are on the relationship between the two. You reflect on how early physics never treats distance and duration as isolated entities. They appear together in every experiment. Even when mathematicians label them separately, practical measurement keeps them linked. You cannot observe one without the other changing. You feel how this understanding remains calm and grounded. There is no need for abstraction yet. The lesson is observational. Motion reveals structure. The universe behaves consistently enough that relationships can be trusted. This trust grows slowly, through repetition. You consider how acceleration adds depth to the picture. When speed changes, distance accumulates differently over time. This requires more careful tracking, but the relationship remains intact. Change itself becomes measurable only through the joint behavior of space and time. You notice that even rest depends on this framework. An object at rest remains in the same position as time passes. Its lack of motion is still defined relative to duration. Without time passing, rest cannot be identified. Without space, position cannot be named. Even stillness relies on both. You rest with how quietly convincing this is. Motion does not argue. It demonstrates. Every moving object confirms the same structure. Distance unfolds through time. Time reveals itself through change in position. Neither stands alone in practice. You sense that this realization prepares the ground for deeper ideas. If motion always binds space and time, then treating them as entirely separate may be an assumption rather than a necessity. The evidence does not demand separation. It suggests connection. You remain calm with this thought, allowing it to settle gently. Motion continues everywhere, from drifting clouds to orbiting planets. Each movement carries the same quiet message. Where something is cannot be fully known without knowing when it is there. When something happens cannot be understood without knowing where it occurs. In this steady observation, the foundation is laid for a more unified view of how reality measures itself. You settle into a universe that feels steady and reliable. In this view, space stretches outward in all directions, unchanged and unmoving. Time flows forward at a constant rate, the same everywhere for everyone. This is the framework Isaac Newton introduces, not as speculation, but as a practical structure that fits the observations of his era with extraordinary success. You imagine space as a vast, fixed reference. Objects move through it, but space itself does not respond. It does not bend, shift, or depend on what occupies it. Whether empty or filled, it remains the same. Positions can be measured absolutely, even if no object is nearby to mark them. This idea feels natural because it aligns with everyday experience. A room seems to exist whether or not you are inside it. You notice how time is treated with the same independence. Time passes uniformly, second after second, unaffected by motion or location. A clock on Earth and a clock in the heavens are assumed to tick at the same rate. Duration does not depend on speed, height, or direction. It simply flows. This assumption allows time to serve as a universal ruler for change. You see how motion fits neatly into this structure. Velocity becomes change in position relative to absolute space, measured against absolute time. Acceleration becomes change in velocity per unit time. Forces act on objects, altering their motion within this fixed framework. The clarity of this system is powerful. It allows prediction, calculation, and explanation with impressive precision. You reflect on why this approach works so well. Everyday speeds are slow compared to the speed of light. Gravitational fields are relatively weak. Under these conditions, measurements behave as if space and time are truly separate. Experiments confirm Newton's equations again and again. Planets follow predictable paths. Projectiles land where calculations say they will. Tides, orbits, and pendulums all obey the same rules. You consider inertia, one of the quiet foundations of this system. An object continues in uniform motion unless acted upon. Uniform motion means constant velocity through absolute space over absolute time. This idea assumes that motion can be defined even without nearby reference objects. Newton imagines a true state of rest and a true state of motion, whether or not they can be observed directly. You notice how gravity fits into this picture. Gravity acts as a force between masses, pulling them toward one another across space. The force depends on distance and mass, not on time itself. Time simply provides the parameter over which motion responds. Space remains the arena, time the clock, and gravity the actor. You rest with how cleanly this arrangement separates roles. Space holds positions. Time measures change. Forces cause motion. Each concept has a clear boundary. This separation makes calculations manageable and intuitive. It reflects how humans naturally categorize experience. You observe how Newton supports these ideas with careful reasoning and experiment. Rotating buckets of water reveal curved surfaces, suggesting motion relative to absolute space. Spinning objects experience forces even when relative motion seems absent. These experiments are interpreted as evidence that space itself provides a reference beyond objects alone. You notice that for centuries, this framework faces little challenge. Engineering, navigation, astronomy, and mechanics all rely on it successfully. Bridges stand. Cannons fire accurately. Planets return on schedule. There is no urgency to question the foundations when predictions continue to match observation so well. You begin to sense where subtle tension quietly appears. Light behaves oddly within this system. Its speed seems unaffected by the motion of its source. Attempts to measure motion through space using light fail repeatedly. These results are puzzling, but they do not immediately overturn the framework. They linger as unresolved details. You reflect on how absolute time quietly assumes simultaneity. Two events occurring at the same time are simultaneous everywhere. This assumption feels obvious because it matches daily experience. Yet it depends on time flowing identically throughout space. Without absolute time, simultaneity becomes uncertain. You notice that Newton himself remains cautious. He distinguishes between relative measures and absolute reality. What is measured may differ from what truly exists. Absolute space and time provide the underlying truth, even if they cannot be directly observed. This philosophical move preserves the structure while acknowledging practical limits. You feel the calm confidence of a system that explains much of the visible world. There is no drama here, only consistency, reliability, and predictive power. Space and time stand apart, stable and universal, offering a dependable stage for motion to unfold. You rest with the understanding that this framework does not fail outright. It remains accurate within a wide range of conditions. Even today, it is used when precision demands are modest. The success is real and measurable. Yet a quiet question lingers. If space and time are truly absolute, then every observer should agree on distances and durations, regardless of motion. Some observations begin to suggest this agreement may not always hold. The discrepancies are small, subtle, and easy to overlook, but they persist. You allow this thought to remain gentle and unresolved. Newton's universe remains calm, orderly, and deeply useful. But within its precision, the possibility arises that space and time may not be as independent as they appear, especially when observation reaches beyond the familiar scales of everyday motion. You bring your attention to light, not as something mysterious, but as something measurable. Light travels, reflects, refracts, and can be timed with increasing precision. For centuries, it behaves like any other physical phenomenon, expected to follow the same rules as moving objects. Yet as measurements improve, light begins to reveal something unexpected. You notice that light always moves extremely fast, but speed alone is not the issue. What matters is consistency. No matter how carefully observers measure it, the speed of light appears the same. It does not seem to add or subtract speed based on the motion of its source. This result is not dramatic at first. It is simply persistent. You consider how classical physics expects speeds to combine. If you move toward a sound source, the sound reaches you sooner. If you move away, it reaches you later. The speed of sound depends on the motion of the observer through air. By analogy, light should behave the same way if it moves through some medium. Early physics assumes such a medium must exist. You learn that this hypothetical medium is called the luminiferous ether. It is imagined as a substance filling all of space, providing a reference frame for light's motion. Light is thought to ripple through it, much like waves through water. This idea preserves absolute space while explaining how light travels. You observe how scientists attempt to detect motion through this ether. If Earth moves through it, then light traveling in different directions should have slightly different speeds. Careful instruments are built to test this expectation. The goal is simple. Measure a difference. You follow the Michelson-Morley experiment, not as a dramatic event, but as a careful procedure. Light beams are split, sent along perpendicular paths, and recombined. Any difference in speed should produce a measurable shift. The experiment is repeated at different times of year, as Earth changes direction in its orbit. The setup is refined again and again. You rest with the result. No shift appears. The speed of light remains the same in every direction. This outcome is not noisy or uncertain. It is steady and repeatable. The ether, if it exists, leaves no detectable trace. You notice that this is not a single failure. Other experiments confirm the same thing. No matter how Earth moves, light behaves as though its speed is fixed. The universe offers no preferred state of rest for light. This behavior does not fit easily into Newton's framework. You feel the quiet discomfort this creates. If space is absolute, then motion through it should be measurable. If time is absolute, then speeds should add predictably. Light refuses to cooperate with these assumptions. Yet the measurements are trustworthy. The instruments work. The procedures are sound. You consider possible adjustments. Perhaps the ether is dragged along with Earth. Perhaps measuring rods shrink in motion. Perhaps clocks behave oddly. These ideas begin as patches, not replacements. Each attempt preserves absolute space and time at the cost of increasing complexity. You notice how the idea of simultaneity begins to feel fragile. Measuring the speed of light requires synchronized clocks at different locations. But synchronizing clocks already assumes something about how time flows. If light is used to synchronize them, then its constant speed becomes part of the definition of time itself. You reflect on how this subtly reverses the logic. Instead of time defining motion, motion through light may define time. This is not yet a conclusion, but the direction is clear. The foundations are shifting. You remain grounded in observation. Nothing mystical occurs. Light simply behaves in a way that does not respect the separation of space and time. The universe is not contradicting itself. Human assumptions are being tested. You observe that these issues become unavoidable as precision increases. At everyday speeds, differences are too small to matter. At the scale of light, assumptions must be exact. Nature responds only to accuracy. You consider how this moment is not a rejection of Newton's work. His equations still predict motion correctly in nearly all ordinary situations. The conflict appears only when pushing measurement to its limits. This is not failure. It is refinement. You feel how calmly the evidence accumulates. There is no sudden collapse of understanding. Instead, there is a growing awareness that something deeper governs reality. Light does not merely move through space over time. Its behavior hints that space and time may be linked more tightly than previously thought. You rest with this realization gently. The universe has not changed. Only the description begins to feel incomplete. Light acts as a messenger, carrying information across space while revealing constraints on time itself. You allow this idea to remain open and unresolved. Light does not explain the answer yet. It only shows that the question must be asked differently. The measurements remain firm, the observations repeatable, and the need for a new way of thinking becomes quietly unavoidable. You rest with the measurements that refuse to change. Light always moves at the same speed, no matter how fast the source or observer travels. This fact is not negotiable. It appears in every careful experiment. Instead of forcing light to obey older assumptions, Einstein chooses a quieter approach. He lets the evidence speak first. You begin with two simple principles. The laws of physics work the same in all uniformly moving frames. The speed of light in a vacuum is constant for all observers. These statements sound modest, but they reach deeply. They do not add new forces or substances. They remove assumptions instead. You notice what must change if both principles are true. If light speed is fixed, then observers moving relative to one another cannot agree on distance and duration in the same way. Something has to give. Einstein allows space and time themselves to adjust. You imagine two observers moving steadily past one another. Each carries a clock and a measuring rod. Each performs careful experiments. Neither is privileged. Each finds the speed of light to be the same. To make this possible, their measurements of time and distance cannot match exactly. This difference is not an illusion or a mistake. It is a physical effect. You observe how time becomes flexible. A clock moving relative to you ticks more slowly than one at rest beside you. This is not because it malfunctions. It is because time itself flows differently depending on motion. Experiments later confirm this effect with atomic clocks and fast-moving particles. You notice how space responds as well. Objects moving relative to you are shorter along the direction of motion. This contraction is not caused by pressure or force. It arises naturally from how distances must be measured when light speed remains constant. Space adjusts to preserve the rule. You reflect on how calm and exact these changes are. They follow precise mathematical relationships. Nothing stretches or slows arbitrarily. The effects become noticeable only at very high speeds, close to the speed of light. At everyday speeds, they are too small to detect. You consider simultaneity, once taken for granted. Events that appear simultaneous to one observer may not be simultaneous to another in motion. This is not due to signal delay or error. It is built into how time is structured. There is no single universal present moment shared everywhere. You remain grounded in observation. These ideas are not philosophical preferences. They are consequences of measurements already made. Einstein does not speculate about what might exist. He accepts what is observed and reshapes the framework to fit it. You notice that space and time are no longer independent backgrounds. They respond to motion together. Change one and the other changes as well. Velocity links them tightly. Motion becomes the key that connects distance and duration into a single system. You see how this preserves consistency. No observer ever measures light traveling faster or slower. No physical law changes between steady frames of motion. The cost is abandoning absolute space and absolute time. The benefit is coherence. You reflect on how this does not erase Newton's work. At low speeds, the differences vanish. Space and time appear absolute because the effects are too small to notice. Newton's equations remain excellent approximations. They emerge naturally from the new framework under familiar conditions. You consider experimental confirmation. Muons created high in Earth's atmosphere reach the ground because their internal clocks run slower relative to Earth. Particle accelerators rely on time dilation to predict behavior accurately. These are not abstract tests. They are practical necessities. You feel how gently this insight changes perspective. Space is not just where things are. Time is not just when things happen. Both depend on how motion unfolds. Neither stands alone as a fixed stage. You remain calm with how little is added and how much is clarified. There is no hidden substance, no undetectable ether. Only relationships remain. Measurements depend on motion, and motion is measured through space and time together. You notice that this framework treats all observers fairly. No one carries a special clock or ruler. The universe does not favor rest over motion. Only relative movement matters. This symmetry feels quiet and stable. You rest with the realization that this insight does not complicate reality. It simplifies it. Two assumptions replace many patches. The behavior of light becomes natural instead of strange. Space and time respond exactly as needed. You sense how this prepares the ground for something larger. If space and time change together with motion, then perhaps they are not separate entities at all. Perhaps they form a single structure whose behavior becomes visible only when pushed beyond everyday experience. You allow this thought to settle softly. Motion no longer moves through space and time as independent things. It reveals how deeply connected they already are, waiting patiently to be measured with enough care. You settle into a shift that feels subtle but profound. Space and time no longer behave as separate containers for events. They form a single structure that holds everything that happens. This structure does not replace observation. It emerges directly from it. You begin by noticing how events are described. An event is not just something that happens. It happens somewhere and sometime. A flash of light, a ticking clock, a collision of particles. Each requires a location and a moment. Without both, the description is incomplete. You recognize that this pairing is not optional. If two observers move relative to one another, they may disagree on distances and durations, but they can still agree that an event occurs. The event itself remains fixed within a larger framework that accounts for both measurements together. You learn that this framework is called spacetime. It is not a substance and not an abstraction detached from measurement. It is a way of organizing physical reality that matches how observations behave. Each event occupies a point within spacetime, defined by 3 spatial coordinates and 1 time coordinate. You notice that treating space and time together removes confusion. Instead of asking whether space changes or time changes, you describe how spacetime behaves. Motion becomes a path through spacetime rather than movement through space alone. You imagine tracing your own presence. As time passes, you move forward along a path. Even when you sit still, you continue progressing through spacetime. This motion is steady and unavoidable. It defines existence itself. You observe how diagrams help clarify this idea. When time is plotted alongside space, motion appears as lines rather than points. Faster motion tilts these lines differently. Slower motion tilts them less. These representations are not artistic tools. They reflect mathematical relationships confirmed by experiment. You reflect on how distances in spacetime are measured. The separation between two events is not defined by space alone or time alone. It depends on both. This combined measure remains consistent even when observers disagree on individual components. This consistency reveals spacetime as a real structure, not a convenient label. You notice that the speed of light plays a central role. Light travels along paths that define the geometry of spacetime itself. Because its speed is constant, it sets the scale that links space and time. One cannot change without affecting the other. You remain grounded in evidence. Particle physics experiments track paths through spacetime every day. Detectors record when and where interactions occur. Predictions rely on spacetime relationships to match observations precisely. Without this framework, the data would not align. You consider how causality fits naturally here. Causes come before effects within spacetime. Signals cannot travel faster than light. This limit preserves consistent ordering of events for all observers. Spacetime enforces structure without preference. You notice that spacetime is not static. It responds to motion and energy. But even before considering gravity, its unified nature already shapes reality. The separation of space and time becomes an approximation, useful only under limited conditions. You reflect on how this idea remains calm and restrained. Nothing mystical is added. There is no hidden realm. Only relationships that measurements demand. The universe behaves as though space and time are woven together, because they are. You feel how this simplifies understanding. Instead of tracking two separate entities, you follow one structure. Motion, causality, and measurement align naturally. Conflicts dissolve when assumptions are adjusted. You observe that this structure does not depend on human perspective. It exists whether or not it is described. Observers move through it, record it, and test it. The results remain consistent. You remain aware that spacetime does not remove mystery. It replaces confusion with clarity. Tells you how reality behaves, not why it exists. It sets boundaries that experiments respect. You rest with how quietly this idea settles. Events do not float in empty time or drift through passive space. They are anchored within a unified framework that holds position and duration together. You sense that this framework invites further exploration. If spacetime is real and physical, then it may respond to matter and energy. It may curve, stretch, or change shape under extreme conditions. You allow this awareness to remain gentle. The universe has revealed a deeper layer of order without raising its voice. Space and time are no longer separate stages. They form a single, steady structure that supports everything you observe, waiting patiently to show how it responds when motion becomes extreme and gravity grows strong. You allow your attention to rest on speed, not as effort or force, but as motion measured carefully. At low speeds, time feels steady and distances feel fixed. Nothing seems to change when you walk, ride, or fly. But nature does not stop obeying its deeper rules just because the effects are too small to notice. As speed increases, those rules begin to reveal themselves. You begin with time because timekeeping is precise. Modern clocks measure time using regular physical processes, such as the vibration of atoms. These clocks do not rely on human perception. They count events with extraordinary accuracy. When such clocks are placed in motion at very high speeds, something subtle happens. They tick more slowly compared to clocks at rest. You notice that this slowing is not caused by mechanical stress or malfunction. The clocks work perfectly. Each clock behaves normally in its own frame of motion. The difference appears only when their readings are compared. This difference is called time dilation, and it follows exact mathematical relationships predicted by relativity. You consider how this has been tested. Atomic clocks are flown aboard fast-moving aircraft and later compared with identical clocks on the ground. The moving clocks show slightly less elapsed time. The difference is tiny but measurable. The result matches predictions precisely. Repeated experiments confirm the same outcome. You observe the same effect in particle physics. Unstable particles created at high speed survive longer than expected when observed from the laboratory frame. Their internal processes slow down relative to stationary observers. Without time dilation, many particles would decay before reaching detectors. Their observed survival is direct evidence that time itself behaves differently at high speed. You remain calm with this idea. Time does not slow universally. It slows relative to another frame of motion. Each observer experiences their own time normally. The effect appears only when comparing clocks moving differently. There is no absolute slowdown, only relative change. You now turn to space. Just as time adjusts, distance adjusts as well. Objects moving at high speed become shorter along the direction of motion when measured by a stationary observer. This effect is called length contraction. Like time dilation, it is not caused by physical compression. It arises from how distances must be measured when light speed remains constant. You imagine measuring the length of a fast-moving object. To determine its length, you must record the positions of both ends at the same time. But simultaneity depends on motion. What counts as the same time for one observer does not match another's definition. This difference leads naturally to shorter measured lengths. You notice that this contraction affects only the direction of motion. Widths and heights remain unchanged. The effect becomes noticeable only at very high speeds. At everyday speeds, the contraction is far too small to detect. You reflect on how time dilation and length contraction work together. As an object moves faster, time slows and space shortens in just the right proportion to preserve the constant speed of light. These effects are not independent adjustments. They are coordinated responses within spacetime itself. You remain grounded in evidence. Particle accelerators must account for both effects to function correctly. Without length contraction, circulating particles would not fit predicted paths. Without time dilation, their behavior would not match observed lifetimes. The technology works because the physics is correct. You consider how this challenges everyday intuition. It may feel strange that motion alters time and distance, but intuition is shaped by slow speeds and weak fields. Nature does not adjust its rules to match comfort. It follows consistency. You notice that no observer ever measures themselves as shortened or slowed. Each observer always finds their own clock ticking normally and their own ruler unchanged. The effects appear only in comparison. This preserves internal consistency and removes paradox. You rest with how carefully these changes are balanced. There is no tearing or distortion. Spacetime responds smoothly. As speed increases, adjustments increase predictably. Nothing abrupt occurs. You observe that these effects do not depend on how motion began. Whether an object accelerates or has always moved at high speed, the measurements depend only on relative velocity. This reinforces the idea that spacetime structure governs behavior, not history. You consider how this understanding explains earlier puzzles. Light's constant speed no longer appears strange. Measurements adapt so that no observer ever sees light violate its rule. Space and time change just enough to maintain consistency. You feel how calm the universe remains under this description. There is no contradiction, only coordination. Space and time are not rigid frameworks resisting motion. They are flexible aspects of a unified structure responding to it. You remain aware that these effects grow stronger as speed increases. Near the speed of light, time slows dramatically and lengths contract significantly. These conditions are rare in daily life but common in cosmic and subatomic environments. You allow yourself to rest with the idea that motion reveals the structure of spacetime more clearly at extremes. At gentle speeds, the structure hides behind approximations. At high speed, it becomes visible. You sense that this realization deepens understanding rather than complicating it. The universe behaves consistently at all speeds. The rules simply become more apparent when motion is extreme. You remain calm with the knowledge that time and space are not fixed backdrops. They respond together quietly and precisely whenever speed demands it. In this steady behavior, spacetime shows itself not as an idea, but as a measurable structure that adjusts smoothly as motion approaches its natural limits. You rest your attention on gravity, something you feel constantly but rarely question. Objects fall. Planets orbit. Stars hold together. For centuries, gravity is described as a force pulling masses toward one another across space. This description works well, but careful measurement begins to suggest a deeper explanation, one that removes pulling altogether. You begin by noticing a simple fact. When you drop an object, it accelerates downward at the same rate regardless of its mass. A stone and a feather fall together when air resistance is removed. This behavior is unusual for a force. Forces usually depend on mass. Gravity does not, at least not in this way. You reflect on how this observation quietly unsettles classical thinking. If gravity were a force acting on mass, different masses might respond differently. Instead, everything follows the same path when falling freely. This consistency hints that gravity may not be something acting on objects, but something shaping their motion. You consider Einstein's approach. Instead of asking what force pulls objects downward, he asks how objects move when no force acts on them at all. In physics, this kind of motion is called free motion. Objects move along paths that require no effort, guided only by the structure of the space they occupy. You notice how this idea applies to spacetime. If spacetime itself is curved, then objects moving freely will follow curved paths. They are not being pulled. They are simply following the natural geometry around them. This is the core insight. Gravity is not a force transmitted across space. It is the shape of spacetime itself. You imagine spacetime as something that can be measured and described. Mass and energy change its geometry. Where spacetime is flat, objects move in straight paths. Where it is curved, those paths bend. The bending appears to observers as acceleration. You observe how this explains falling objects. When you drop something, it is not being pulled downward by an invisible force. It is following the straightest possible path through curved spacetime. To you, standing on Earth, that path looks like downward acceleration. You remain grounded in observation. This idea is not introduced to sound elegant. It arises because it matches evidence more closely than the force-based picture. It explains why all objects fall the same way. It explains why gravity affects time as well as space. You notice how planetary orbits fit naturally here. Planets move freely through curved spacetime shaped by the sun's mass. Their paths are not circles pulled by force. They are curved trajectories that reflect spacetime's geometry. This description reproduces known orbits with precision. You reflect on how this model explains small discrepancies classical gravity cannot. The orbit of Mercury shifts slightly over time in a way Newton's theory cannot fully predict. Spacetime curvature accounts for the difference exactly. Observation confirms the prediction. You consider light, which has no mass. In a force-based view, gravity should not affect it. Yet observations show that light bends when passing near massive objects. This bending is measured during solar eclipses and through precise astronomical observations. Light follows curved spacetime just like everything else. You notice how this confirms the idea strongly. If gravity were a force acting on mass, light would not respond. If gravity is geometry, light responds naturally because it moves through spacetime itself. The evidence favors geometry. You remain calm with how spacetime responds to energy as well as mass. Pressure and motion also shape curvature. This means gravity is not static. It evolves with the distribution of energy in the universe. Spacetime is dynamic, not fixed. You observe how clocks behave near massive objects. Time passes more slowly closer to Earth than farther away. This is not caused by motion alone. It is caused by gravity. Atomic clocks confirm this difference directly. Without accounting for it, satellite systems would fail. You reflect on how gravity affecting time reinforces the idea of unified spacetime. Space and time cannot be treated separately if gravity alters both. Curvature involves the full structure, not just spatial dimensions. You consider free fall again. Astronauts orbiting Earth feel weightless, not because gravity disappears, but because they are moving freely through curved spacetime. They follow the natural path without resistance. Weight arises only when something prevents free motion. You notice how this explanation removes mystery rather than adding it. Gravity is not an invisible pull reaching across emptiness. It is a property of spacetime that can be calculated, predicted, and tested. The equations describe how curvature responds to energy and how motion responds to curvature. You remain aware that this view does not deny experience. Falling still feels like falling. Orbits still look like attraction. The difference lies in interpretation, not outcome. Geometry replaces force as the underlying cause. You observe how this framework scales from everyday gravity to extreme environments. Near massive stars and black holes, spacetime curvature becomes intense. Paths bend sharply. Time slows dramatically. Observations of stars orbiting unseen massive objects confirm these predictions. You rest with how quietly successful this picture is. It explains gravity without adding new substances or hidden mechanisms. It builds directly on the idea that spacetime is real and physical. You notice that gravity no longer fits into the same category as other forces. It is not something happening within spacetime. It is spacetime itself responding to what it contains. This distinction matters deeply. You allow this understanding to remain gentle. There is no need to visualize dramatic shapes. The curvature is mathematical, precise, and measurable. Its effects appear only through motion and time. You sense that this idea reshapes how you think about motion entirely. Objects do not struggle against gravity. They move along the path spacetime provides. Resistance, support, and acceleration arise only when motion is constrained. You remain calm with how consistent this picture is. From falling apples to bending light, the same structure applies. Evidence from laboratories, satellites, and distant stars all align. You rest with the awareness that spacetime is not only unified but active. It responds to mass and energy, shaping motion in return. In this steady interaction, gravity reveals itself not as a force to be felt, but as the quiet geometry through which all motion naturally unfolds. You settle your attention on measurement, because measurement leaves little room for interpretation. Ideas about spacetime are not supported by thought alone. They are tested continuously by instruments that count, compare, and repeat. Among the most reliable of these instruments are clocks. You begin with modern atomic clocks. These clocks measure time using the natural vibration of atoms, a process that repeats with extraordinary regularity. Their precision is so high that differences of billionths of a second can be detected. When clocks this accurate disagree, the disagreement matters. You observe that when atomic clocks are placed in different conditions, they do not remain synchronized. A clock on Earth's surface ticks slightly more slowly than a clock placed higher above the planet. This difference is not caused by temperature or mechanical disturbance. It persists even under controlled conditions. The explanation lies in gravity. You recall that gravity affects time. Clocks closer to Earth's mass experience stronger spacetime curvature. Time passes more slowly there. This effect is small but measurable. Experiments compare clocks separated by only a few meters in height and detect consistent differences. The results match predictions exactly. You notice that motion adds another layer. A clock moving rapidly relative to Earth ticks more slowly than one at rest on the surface. This effect comes from speed alone. When both gravity and motion are present, their effects combine. Each influence can be calculated and tested independently. You consider clocks carried aboard aircraft. When flown around the planet and compared with ground-based clocks, they show measurable differences in elapsed time. These differences depend on direction, speed, and altitude. The results are not random. They align precisely with spacetime predictions. You remain calm with how direct this evidence is. There is no interpretation required. The clocks either agree or they do not. They do not agree, and the disagreement is exactly what theory predicts. You shift your attention upward, toward satellites orbiting Earth. These satellites carry atomic clocks as well. They move quickly and reside in weaker gravitational fields than clocks on the ground. Without correction, their timekeeping would drift rapidly out of sync with Earth-based systems. You notice that global navigation systems rely on these satellites. Each satellite broadcasts time signals that receivers use to calculate position. The calculation depends entirely on accurate timing. An error of a few billionths of a second translates into meters of error on the ground. You observe that spacetime corrections are built directly into these systems. Engineers adjust satellite clocks to account for both gravitational time dilation and motion-based time dilation. If these corrections were removed, navigation errors would grow by kilometers each day. The system works because spacetime effects are real. You reflect on how this evidence does not come from exotic experiments. It comes from technology used daily. Navigation, communication, and synchronization all depend on accurate timekeeping across different conditions. Spacetime behavior is not theoretical here. It is operational. You consider orbits themselves. Satellites follow predictable paths around Earth. These paths are calculated using spacetime geometry, not simple force diagrams. Corrections for relativistic effects ensure long-term stability. Observations confirm the calculations repeatedly. You notice how planetary orbits show similar precision. The motion of planets around the Sun matches predictions that include spacetime curvature. Small deviations that cannot be explained by classical gravity are accounted for accurately when spacetime effects are included. Observation confirms the match. You turn your attention to Earth itself. The planet rotates, bulges slightly at the equator, and carries clocks at different speeds and elevations. Precise timing networks must account for all of this. Time is not uniform across the surface. Spacetime varies gently but measurably. You remain grounded in how quietly this variation exists. No sensation accompanies it. You do not feel time slow or speed up. Only careful measurement reveals the difference. The universe does not announce its structure. It allows it to be discovered. You observe that these effects accumulate. Over short periods, differences are tiny. Over long periods, they become significant. This accumulation is what allows detection and verification. The longer the measurement, the clearer the result. You reflect on how this reinforces earlier insights. Space and time are not separate backgrounds. They respond to gravity and motion together. Clocks reveal time's flexibility. Orbits reveal space's curvature. Both respond to the same underlying structure. You notice that none of this depends on interpretation or belief. Engineers do not debate whether spacetime effects exist. They calculate them. Systems either function or fail. The success of modern technology confirms the correctness of the framework. You consider how these measurements scale outward. Signals traveling between Earth and distant spacecraft must account for spacetime delays. Tracking probes across the solar system requires precise models of how time and space behave. Missions succeed because these models work. You remain calm with how consistent the evidence is. From laboratories to satellites to planets, the same principles apply. No contradictions appear, only refinement. You feel how this steadiness deepens understanding. Spacetime is not revealed by dramatic events alone. It reveals itself through careful comparison, steady observation, and patient correction. You rest with the awareness that clocks and orbits do more than measure time and motion. They reveal the structure that governs both. They show that spacetime is not an abstract idea layered onto reality. It is the framework within which reality operates. You allow this realization to settle gently. The evidence does not shout. It accumulates quietly, second by second, orbit by orbit. Through precision and repetition, Earth and space together confirm that space and time are woven into a single, measurable structure that guides motion with calm reliability. You let your attention widen outward, away from local motion and nearby gravity, toward the universe as a whole. When you look far enough into space, you are also looking back in time. Light from distant galaxies takes millions or billions of years to reach you. Distance becomes a record of duration. Space itself carries history. You notice that galaxies are not fixed in place. Careful observation shows that most distant galaxies are moving away from Earth. The farther away a galaxy is, the faster it appears to recede. This relationship is not random. It is measured repeatedly using the redshift of light, where wavelengths stretch as space expands. You understand that this motion is not like galaxies flying through empty space. Instead, space itself is expanding between them. The galaxies are largely at rest within their local regions, while the distances between regions grow. This distinction matters. It tells you that space is dynamic, not static. You rest with how this expansion is measured. Astronomers compare the known properties of light emitted by atoms with what is observed from distant galaxies. The stretching of light directly reflects the stretching of space. The measurement does not depend on assumptions about motion alone. It reflects geometry. You notice that if space is expanding now, it must have been smaller in the past. Reversing the expansion mathematically leads to a state where distances shrink toward zero. As space contracts, time moves backward toward a boundary. This boundary is not a place within space. It is a moment in time where the expansion begins. You recognize that this moment is called the beginning of the universe, often referred to as the Big Bang. It is not an explosion occurring at a point in space. It is the expansion of space itself from an earlier, denser state. Everywhere expands at once because everywhere is space. You remain grounded in observation. This conclusion does not come from imagination. It arises from measured expansion, cosmic background radiation, and the abundance of light elements. These independent lines of evidence converge on the same picture. You consider the cosmic microwave background. This faint radiation fills all of space and arrives uniformly from every direction. It is the cooled remnant of a time when the universe was much hotter and denser. Its existence confirms that the universe evolves over time and that space itself has a history. You notice that this radiation does not come from a distant location. It comes from all directions equally. This uniformity shows that the early universe was once small enough for conditions to be shared everywhere. Space and time emerge together from that state. You reflect on how element formation supports this view. Hydrogen, helium, and traces of lithium form in precise ratios during the universe's early moments. These ratios depend on both temperature and timing. Observations match predictions closely. The clock of the universe leaves chemical evidence. You remain calm with the implication. If space and time emerge together, then asking what came before time loses meaning. Time itself is part of the structure that begins. There is no earlier moment in the same way there is no location outside space. You notice how this reframes the idea of origin. The beginning is not embedded within spacetime. It is the boundary of spacetime itself. Space does not expand into something. Time does not flow from something earlier. Both unfold together from a shared starting point. You consider how this picture removes the possibility of separating space and time at the largest scale. The universe does not begin with space first and time later. They are inseparable from the start. Every moment of cosmic history carries both. You observe how this understanding is tested continuously. Measurements of galaxy distribution, expansion rate, and cosmic radiation refine the timeline. The details improve, but the core picture remains stable. Space has expanded. Time has passed. Both are linked. You reflect on how expansion affects time itself. As the universe expands, conditions change. Temperatures drop. Structures form. Time becomes meaningful only because change occurs within expanding space. Without space evolving, duration would have no context. You remain grounded in the present moment. Even now, space continues to expand. Distant galaxies drift farther away. The universe carries its past within its structure. Time is not an external parameter ticking independently. It is woven into cosmic evolution. You notice that this expansion is measured locally and globally. Nearby galaxies move slowly. Distant ones move faster. The pattern remains consistent. Space behaves the same way everywhere on large scales. Time tracks that behavior. You consider how this reinforces earlier insights. Motion links space and time. Light reveals their connection. Gravity curves them together. Now cosmology shows they begin together. The pattern is consistent across scales. You remain calm with how little assumption is required. The universe offers its history through observation. Space stretches. Light redshifts. Radiation cools. Elements form. Each piece aligns. You feel how this understanding removes the temptation to imagine time as something flowing independently of the universe. Time is not an external backdrop. It is part of the universe's structure, emerging and evolving with space itself. You rest with the awareness that the universe carries its origin quietly. There is no edge to find, no center to point to, only expansion that links distance and duration inseparably. You allow this thought to settle gently. Space and time are not stitched together later by theory. They are born together, revealed together, and measured together. The universe does not permit one without the other, and its earliest light still carries that message across the vast distances you observe today. You allow your attention to move toward environments where gravity no longer feels gentle. In most places, space-time curves only slightly. Near Earth, the effect is subtle. Near stars, it grows stronger. But near a black hole, Spacetime reaches an extreme state that exposes its unified nature more clearly than anywhere else. You begin with how black holes form. When a massive star exhausts its nuclear fuel, it can no longer support itself against gravity. The star collapses inward. If the remaining mass is large enough, no known force can stop the collapse. Space and time respond together as matter compresses into an incredibly small region. You notice that a black hole is not defined by its material surface. It is defined by a boundary in spacetime called the event horizon. This boundary marks the point beyond which light can no longer escape. The definition itself already links space and time, because escape depends on motion through spacetime. You reflect on what happens near this boundary. As you approach a black hole from far away, gravity grows stronger. Paths through space curve sharply. Time slows dramatically relative to distant observers. Clocks closer to the black hole tick more slowly, not because they malfunction, but because spacetime itself is altered. You remain grounded in observation. Astronomers do not see black holes directly, but they see their effects. Stars orbit unseen massive objects at tremendous speeds. Their orbits reveal intense curvature. The motion matches predictions made using spacetime geometry, not force-based shortcuts. You consider light near a black hole. Light follows the straightest possible paths through spacetime, yet those paths bend strongly near extreme curvature. Observations show light from background stars bending around massive objects. In the case of black holes, this bending becomes dramatic, producing rings and arcs of light that can be measured. You notice that light can orbit a black hole under precise conditions. This does not mean light is trapped by force. It follows curved spacetime paths that close in on themselves. The geometry alone determines the motion. You rest with how time behaves in these regions. From far away, an object falling toward a black hole appears to slow as it approaches the event horizon. Signals arrive more slowly and with increasing redshift. Time seems to stretch outward. This effect is not an illusion. It reflects how spacetime connects distant regions. You remain careful with perspective. For the falling object itself, nothing special happens at the horizon. Its own clock ticks normally. The extreme behavior arises from comparing clocks in very different gravitational environments. Again, time is not absolute. It is shaped by spacetime geometry. You consider what happens inside the event horizon. While direct observation is impossible, the mathematics remains clear. Paths through spacetime tilt so strongly that all future directions lead inward. Space and time exchange roles in a precise mathematical sense. This is not metaphor. It is a statement about how coordinates behave. You notice that this exchange reinforces inseparability. Inside a black hole, moving forward in time inevitably means moving deeper inward. There is no way to remain at rest. Spacetime structure enforces direction. You reflect on how black holes test the limits of understanding without abandoning evidence. Predictions about their behavior are confirmed through gravitational waves, emitted when black holes collide. These waves ripple through spacetime itself and are detected by sensitive instruments on Earth. You observe that gravitational waves carry information about spacetime curvature changing over time. They are not vibrations traveling through space. They are changes in spacetime. Their detection confirms that spacetime is physical and dynamic, capable of oscillation. You notice how precisely these signals match theoretical predictions. The timing, frequency, and decay align with models based on curved spacetime. No alternative explanation fits the data as well. You remain calm with how black holes unify earlier insights. Motion, light, gravity, and time all respond to the same structure. Nothing acts independently. Space does not curve without affecting time. Time does not slow without spatial consequences. You consider how black holes also influence their surroundings. Gas spirals inward, heating as it accelerates through curved spacetime. The radiation emitted carries signatures that reveal gravitational effects. Observations confirm these patterns repeatedly. You reflect on how this environment leaves no room for separating concepts. To describe what happens near a black hole, you must use spacetime. There is no workable description using space alone or time alone. Both fail without the other. You notice that black holes do not break physical law. They follow it precisely even if conditions become extreme. Predictions remain consistent. Measurements match expectations. The framework holds. You rest with how this extreme case strengthens confidence rather than weakening it. If spacetime were merely a convenient idea, it would fail under stress. Instead, it proves robust when gravity becomes intense. You remain aware that black holes do not represent chaos. They represent order taken to its limit. Geometry governs motion even there. The universe remains lawful. You allow yourself to remain calm with this realization. Black holes do not add mystery by defying understanding. They deepen understanding by revealing structure more clearly. You sense that spacetime shows its true nature most clearly when tested hardest. Under extreme gravity, the connection between space and time becomes undeniable. They no longer appear as separate concepts stitched together. They reveal themselves as one continuous structure shaping every possible path. You rest with the knowledge that black holes are not exceptions to how the universe works. They are confirmations. In their extreme union of space and time, they quietly affirm what gentler environments already suggest, that the universe measures itself through a single, inseparable fabric that remains consistent even at its most intense limits. You rest with a simple question that now feels unavoidable. What happens if space and time are treated as separate, independent entities? For centuries, this separation feels natural and harmless. Yet as measurements become more precise, the separation begins to fail quietly but consistently. You begin by noticing how prediction depends on consistency. Physics works because the same rules apply everywhere, every time. When space and time are treated independently, observers moving differently should still agree on outcomes. But observation shows they do not. Distances change. Durations change. Treating these changes as errors only multiplies contradictions. You consider light again, because light exposes inconsistency immediately. If time is universal and space is fixed, the speed of light should vary depending on motion. It does not. Insisting on separation forces increasingly complex explanations that do not improve accuracy. The evidence resists simplification in the wrong direction. You observe how simultaneity becomes undefined under separation. If time flows the same everywhere, then distant events should have an agreed order. Yet experiments show that observers in motion do not agree on which events occur at the same time. This disagreement is not due to delay or miscommunication. It is structural. You remain grounded in the role of clocks. Clocks measure time through physical processes. When clocks in different motions or gravitational fields disagree, the disagreement is real. Treating time as independent forces one to claim that clocks malfunction systematically. That claim fails under repeated testing. You reflect on how separation breaks causality. Cause and effect rely on consistent ordering of events. Without spacetime unity, different observers could disagree on causal order in ways that allow contradictions. Spacetime structure prevents this by enforcing light speed limits and consistent event relationships. You notice how particle physics depends on spacetime unity. Collisions, decays, and interactions are described using spacetime intervals. These intervals remain consistent across observers even when space and time components change. Without this invariant structure, predictions collapse. You consider gravity. If space alone curves while time remains unaffected, gravitational effects on clocks would not occur. Yet clocks near massive objects tick differently. Ignoring time curvature produces incorrect predictions that do not match observation. Gravity acts on spacetime, not space alone. You observe how separation fails technologically. Navigation systems, satellite communication, and synchronization rely on relativistic corrections. Treating time as universal would cause systems to drift rapidly. The corrections are not optional adjustments. They are required for function. You remain calm with how these failures appear not as dramatic contradictions, but as steady mismatches. Predictions become slightly wrong. Errors accumulate. Precision collapses quietly rather than loudly. Physics does not shatter. It erodes. You reflect on how spacetime unity restores simplicity. Instead of forcing separate corrections for space and time, one unified framework explains all effects at once. Motion, gravity, light, and causality align naturally. Fewer assumptions produce more accurate results. You notice that this unity does not eliminate classical ideas. At low speeds and weak gravity, spacetime behaves almost as though space and time are separate. The separation works as an approximation. The mistake is treating the approximation as fundamental. You consider how separation hides relationships. Motion connects distance and duration. Gravity alters both position and time rate. Expansion links cosmic distance with cosmic age. Ignoring these links does not remove them. It only obscures them. You remain grounded in evidence. Every time physics pushes toward higher precision, spacetime unity becomes more important, not less. The deeper the measurement, the clearer the connection. You reflect on how this mirrors earlier scientific shifts. Treating Earth as stationary works until precision improves. Treating heat as a substance works until energy conservation is measured. Separation works until observation demands more. You notice that spacetime unity does not introduce mystery. It removes it. Instead of unexplained discrepancies, there are predictable relationships. Instead of patchwork fixes, there is structure. You rest with how calm this resolution feels. Physics does not demand separation. It demands coherence. Spacetime provides that coherence. You remain aware that insisting on separation forces physics to contradict itself. Measurements disagree. Observers conflict. Predictions fail. None of these problems appear when space and time are treated together. You allow this understanding to settle gently. Space and time are not independent ingredients that must be combined artificially. They are aspects of a single structure revealed through motion, gravity, and measurement. You sense that the universe does not tolerate unnecessary division. It offers relationships instead. Space and time respond together because they are together. You rest with the quiet clarity of this realization. Separating space from time does not simplify reality. It breaks it. Only by allowing them to remain unified does physics remain consistent, predictive, and deeply aligned with what observation continues to reveal. You allow your attention to soften, not by letting go of understanding, but by letting it settle. After following measurement, motion, gravity, and cosmic history, the picture that remains is steady and complete. The universe does not rush to explain itself. It reveals structure patiently, through relationships that repeat and endure. You notice that everything you observe exists somewhere and sometime. No event appears without both. A heartbeat, a falling object, a distant supernova. Each is defined by position and duration together. This pairing is so constant that it fades into familiarity. Yet it never breaks. You reflect on how deeply this structure supports experience. You move through rooms, across landscapes, through days and years. Even rest is motion through time. Even stillness has duration. Space and time do not alternate roles. They operate together continuously. You remain grounded in the fact that this is not a poetic idea. It is an empirical one. Every measurement ever made confirms it. Clocks, rulers, satellites, particles, stars. None of them behave as though space and time exist independently. They respond together, adjust together, and reveal each other. You notice how this understanding changes nothing about daily life, yet explains everything beneath it. You still walk at the same pace. The sun still rises and sets. But beneath those experiences lies a framework that remains consistent across scales, from human movement to cosmic expansion. You rest with how little imagination is required. No unseen realms are introduced. No speculative forces are added. Only what observation demands is accepted. Space and time behave as parts of a single system because measurement leaves no alternative. You reflect on how this system remains calm even under extremes. Near black holes, spacetime curves strongly. Near Earth, it curves gently. At high speeds, it adjusts measurably. At low speeds, it appears steady. The same structure applies everywhere. You notice how this continuity brings quiet reassurance. The universe does not change its rules unexpectedly. It does not behave one way nearby and another way far away. Differences arise from conditions, not inconsistency. You consider how this understanding reframes curiosity. Questions no longer ask how space and time interact. They ask how spacetime behaves under different circumstances. The focus shifts from separation to relationship. You remain aware that this framework does not answer everything. It does not explain why the universe exists or why spacetime has the properties it does. But it explains how the universe behaves with remarkable completeness. Science does not require more than that. You reflect on how knowledge accumulates gently. No single experiment proves spacetime alone. It is the alignment of countless observations that makes the picture unavoidable. Each piece supports the others. Nothing stands in isolation. You notice how this mirrors the structure itself. Space and time are not isolated elements. They are woven together. Evidence, too, is woven together. Understanding emerges from connection rather than separation. You rest with how this realization does not demand effort. It does not require vigilance or constant correction. Once accepted, it simplifies understanding. Motion, gravity, and light no longer compete for explanation. They share one. You observe that even uncertainty fits within this calm. Where knowledge ends, structure remains. The universe may be finite or infinite. Expansion may accelerate. Details continue to refine. None of this threatens the unity already established. You feel how deeply settled this framework is. It does not need defense. It works, predicts. It aligns with observation across centuries and technologies. You remain present with your own position in spacetime. You occupy a location. You experience duration. You move forward steadily. Nothing about this needs interpretation. It simply is. You notice that this presence is not separate from the universe's structure. You are not observing spacetime from outside it. You exist within it. Every thought, breath, and sensation follows its geometry. You rest with how gently this connects personal experience to cosmic order. There is no boundary between everyday life and fundamental physics. The same structure governs both. You consider how this understanding allows rest. There is no need to imagine hidden layers behind reality. What is observed is sufficient. The universe is not incomplete because it is understandable. It is understandable because it is structured. You remain calm with how the story ends without ending. Space and time do not conclude. They continue, measured and connected, supporting every event that occurs. You allow this steadiness to carry your awareness. The universe does not demand attention, provides consistency. Space and time remain woven together, not as an idea to be held tightly, but as a foundation that holds everything else effortlessly in place.